The topic of the webinar today is how the test practitioners, board developers, as well as FPGA developers could benefit from leveraging auto-generated test firmware for testing their boards and ensuring the overall quality of the product shipped to the customers. Right, so our company has started 15 years ago, and we have delivered numerous solutions around the globe. We are presented in many countries, and we have very strong track records also in research. We collaborate with several European universities, as well as we participate in R&D projects globally, and that forms a solid basis for the technologies that become the cornerstone of the instruments we are supplying. If we look at the current trends, global trends, that electronics is taking up more and more space in our life, and even in such traditional mechanical systems like the cars, the cost of electronics is soon to overpass the cost of the rest of the car. So essentially, in the general sense, the quality of electronics is the quality of life for every one of us. And what we can see that the special type of programmable devices, FPGAs, which is the topic of today's webinar, are also becoming ubiquitous. They fill in all the market segments globally, and their usage is growing. So if we look at a typical board today that has an FPGA, it's basically most of the functionality has migrated into these large device, SoC or just an FPGA, or a large microprocessor. These devices, these boards normally have standard periphery and high-speed interfaces. This is the key technological trends that will also define the ways we can test, or we should test these boards in the best possible way. So what are the typical test methods out there? In-circuit test, boundary scan, functional test. Of course, you can apply all of them, but our experience shows that the ability to leverage the functional test to target all the high-speed interfaces, as well as simplify testing of the standard peripheral devices and buses, is actually the key to success. So no board quality, no product quality is really possible without the functional test, FCT. But then the functional test has to be implemented in a careful way that addresses the integration trends. So what we saw before, all functional test strategies were relying on functional testers. So the higher speed, the cards, the higher speed, the equipment you have, the better you can test the board. Today, this is not enough because, as I mentioned, the onboard FPGA contains a lot of actually features is concentrated inside these FPGAs. So leveraging this power, this processing power of onboard FPGA is the key to success for the contemporary functional test strategy. So you actually need to pay more attention to how you program the FPGA, how you develop the test program for the FPGA, that it can be used during the functional test. So, of course, now we have a question. So, who's going to develop the program? Who's going to develop the firmware that will be hosted inside this FPGA? That's a typical board. You can see that it has a lot of peripheral devices, high-speed buses, and the product manager needs to allocate resources. So, the board designer is the person who has just designed the board. He knows the board by heart, so he knows very well how it works, which working modes are there, how to drive bits and bytes, what kind of data to squeeze through high-speed interfaces, what are the timing requirements, what are the non-functional requirements that are imposed to this board. So he basically knows pretty well what needs to be done to the board to have a good test coverage. But now we have a problem. The board has an FPGA, and the board designers normally, they probably can do some simple software parts. The FPGA world is completely different. So the board designer is not the right guy to develop test program. What about test engineer? Of course, the test engineer, just by the job title, has to be capable of doing this, but he faces the same issue. He can write some simple code. He knows how to execute tests, how to put them into a test sequence. He knows how to diagnose, how to troubleshoot, how to find the defects. So he thinks in terms of shorts, opens, top stone defects, missing components, wrong terminations, things like that. And he knows pretty well how to measure the quality of the functional test that has to be developed to test the board. But still, he has very little understanding how to program the FPGA. All right, so we have no other choice than to turn to the superhuman, which is the FPGA developer. And well, he knows very well how to handle these devices like FPGAs, and he knows very well what to do. But he has in his list a lot of other tasks. So he has to close all functional requirements that the product needs to fulfill, the software needs to fulfill. And now the product manager says, all right, we have no other choice. I mean, you need to develop the test firmware. And the FPGA developer thinks, all right, okay, why can't you just use the application firmware for testing purposes? Because, well, anyway, I'm gonna implement this, and you will just have it, just use it for testing. But we all need to remember that test is not an application. So these are completely different worlds. And let me give you some examples. So now the board designer knows whom to talk to. So he comes to FPGA developer and says, all right, we need to verify if the board works. And basically, FPGA developer has the same target. That he needs to verify that his code actually works on the target board. So it's their common grounds to test the product that is coming out from the development. So they need to make sure that the board is working and that the application firmware is working. All right. So, but they're normally facing some difficulties getting to know what is wrong, because the board is fresh. There is no guarantee the board has been implemented fully correctly, that it follows all the requirements. Of course, the board designer has done everything he can, and the FPGA developer has done everything he can to ensure that both the board is working and the FPGA code is working. But still, eventually they need to engage into some sort of a joint debug session where they would eventually struggle to get to know where are the stability problems. Is it a board design issue, or maybe it's an assembly issue? So the prototype has been assembled and it doesn't work stable. So there could be, well, a myriad of problems that make the prototype not working well. So eventually, after a few weeks, it could even take months sometimes, and we've seen some cases like that. They finally come up to the solution. So both of them would benefit from something from somebody else who would say, all right, I can program your FPGA with the correct by construction firmware that you can simply verify your board separately from verifying the FPGA design. And the FPGA developer would also benefit from having a board that has been pre-verified, has been validated before he would run his IPs on this board. So that's important to know. And the product manager says later, hey, well, you know, the hardware release date was just before you started your debug, which is also pretty typical case. Right, now when the board is ready, it has to be tested for production. So production test has to be developed, and now the test engineer comes into the game. And well, he knows whom to turn to. He turns to FPGA developer again and says, all right, give me some test program. And you know what is the key aspect here? The key thing here is that so FPGA developer needs to make sure that his IP is working, his design is working, his software is working, and working is the key word here. And for test engineer, actually the task is different. So he wants to make sure that the board will fail in case there is anything wrong with the board. So the test engineer tries to make everything fail if possible. FPGA developer wants to make everything work as soon as possible. So they have different, they have different targets, they have different challenges they face, and they speak different language. So normally they don't understand each other. So basically, the test engineer, again, he thinks in terms of defects. He says, I want to test for shorts and opens, and the FPGA developer has maybe just a, very basic understanding of what is short and open. What about timestone defects? What about missing termination? What about these kind of things that a test engineer has to address in his test program? So eventually, they come up with something that works, and in the worst case, the FPGA developer will supply a test program that will simply light an LED in the end if everything works. And if some tests failed, so the LED will not light. So that's the very, very funny case, I would say. And that may result in field returns. So that's a headache for the product manager that needs to take this test development cycle from the beginning. So again, something needs to be done for these two guys to make their life easier. And there are some certain drawbacks of using the application firmware that we have learned already. The firmware may not be ready when it's needed, when the test is being developed. Documentation for the firmware may still be missing when it's needed. It may be still incomplete, or maybe some necessary operations modes are missing. Everything results in the lost test coverage, and again, the application is not the test program. If you know any benefits of reusing application firmware in test scenario, drop a line in the comments. Right, so how to solve this issue? Basically, we know all these problems by heart. We worked with our projects, we worked with our customers, and we've been facing all these kind of troubles through the years, and we spent years of research to design and develop a framework that would auto-generate the test firmware for all these guys. And basically, Testonica has all these guys together. They brainstormed and they developed the Quick Instruments platform for functional test and measurement. It has been recognized by a number of studies, and it has been driven by R&D. It's based on patents and so on and so forth. But let's look into what it is, basically, how you can leverage that, how you can benefit from these frameworks. So Quick Instruments would actually provide you with test firmware that is automatically synthesized, the embedded instruments that you may think of embedded instruments as of traditional instruments, signal generators, oscilloscopes, things like that. But imagine them placed inside your board, inside the FPGA. Of course, there are hardware drivers and the related software that is communicating to that instrumentation, onboard instrumentation. And the auto generation process is supported by our sophisticated firmware compilation system that is a result of many years of development. So how can you use? Where is the place for the Quick Instruments framework? Normally, you should apply this, or you should use that framework after the inspection or static test, like AOI, ICT, Flying Probe. If you are using JTAG, you can apply quick instruments after JTAG and before the functional test. Or basically, embedded instruments are very good in fulfilling the job of JTAG and functional test as well. So you can replace these two test steps simply by using quick instruments. And well, the framework is not a service. It means that, I mean, by using framework, you are getting off-the-shelf solution in a very quick, half a day, which automates an amazing amount of tasks. So there have been studies that are showing that 75% or more of productivity gain could be achieved by using these sort of frameworks. So they make sure you do the testing in the right way, using systematic, consistent processes, which are validated on many other customers around the world, and they guarantee the repeatable results. How to use that? So basically, there are several important, application steps or development steps how to use quick instruments. Of course, you need to start from the test target. So what you want to test on your board. Then, based on the test targets, you will get the test core, the embedded instrumentation that implements the testing for your target devices. Then the test engineer will simply integrate everything into his test setup that the test engineer has been using for years. You simply do it again, but in a simple way. Run test and analyze the results. So let's look into a few items and what are the key things around them. Right, so this is a simple example of a complex board, basically. And anyway, a complex board has all the typical things like SPI, flash, SMA, or whatever. I mean the typical components. And if you look into the block diagram of your board, basically all of these devices that are connected to FPGA are covered by the off-the-shelf instruments immediately. So you just get it compiled and run without any debug or anything like that. So eventually, this is the process of getting the test core. Basically, by providing the test targets, the instruments will be fetched from the instrumentation library, off-the-shelf library, compiled using the our backend compilation servers, and released, shipped back to the customer in just a half a day. And you can try that if you like. So what are the key benefits for our poor guys that need to develop validation tests or production tests? So the key advantage is that no FPGA design knowledge is needed, no FPGA design tools are needed, and that creates a tremendous time and cost saving for the product owners. And you see, we don't need to involve FPGA developer at all, because I mean he will concentrate on his tasks. He will keep doing the closing the functional requirements for the application firmware. That's it. It doesn't have to spend time on test development. Right. So and the same test core could be reused on different phases from the board design all the way to test development, down to contract manufacturers. And all of these entities will have clear certain benefits of using this auto-generated test firmware. Eventually, product owner will be the ultimate beneficiary. Now, let's look how the test firmware and the customer firmware or the user firmware, how they interact. So basically, the test firmware is only used during production. It's not gonna stay on your board when the board leaves the factory. It will populate the board when it's fresh, when it's just produced. It will do all the testing. It will do the diagnosis. When it's done, the quick instruments test firmware will load the user application firmware into the board. Will program in a quick way, and it will destroy itself. So the user firmware will stay and will be shipped to the customer. So quick instruments are not keeping any part of the design, and they don't need to be integrated into the user firmware. Okay, so now the challenge of test engineer is, of course, to integrate the whole concept into the test setup. And we are providing, of course, all necessary tools in terms of hardware and software. Most of test setups will work on just very basic cables, USB to JTAG. So the JTAG bus is used to control the instruments. We do also support the high-speed scenarios, like a PXI instrumentation cards could be converted into JTAG, but we don't. We don't offer hardware, so our target is to make everything running on your hardware, not ours. From the software perspective, we are providing an API and the DLL, which are used by the test management software, any test management software that you learn to use and which is convenient for you. So in the end, the test engineer would create a test program that is calling high-level functions through the API. And this API provides a very handy, very easy way to work with target devices on the board. So it's very easy. While running the test, the top performance would be achieved since the FPGA devices on board are very high speed. They would be able to execute the tests at the full functional speed, and as well, the instrumentation allows you to immediately perform some stress testing and performance measurement or performance testing just in the functional test scenario, which is, I would say, unique to this system. You can do it fast and quickly, and in this way guarantee that the test escape rate will vanish. Analyzing the results. Now, of course, it's important to know what kind of defects are targeted by quick instrumentation platform. Anything from the traditional opens and shorts all the way to stability issues of the digital part of your board. Of course, the passive part is not that much addressed. But everything which is connected to FPGA and peripheral devices, all kinds of defects. You can measure the soldering quality indirectly by using these embedded instruments. And it may seem amazing or well unbelievable maybe, but let's bring this discussion into the chat afterwards, or we can have a dedicated meetings about that. Quick instruments are targeting, of course, at-speed test, and they provide quality measurement features as well. But at the same time, we of course able to catch shorts and opens, very classical faults, and check the liveness of the component. So all in all, test engineer needs to optimize the test strategy. How to make sure that the other parts of the board are also covered. So quick instruments are catching quite large part of possible defects, leaving passives to inspection techniques or static test techniques like in-circuit flying probe, as well as if the product owner wants to check the functionality of the device, he may run some application test afterwards. JTAG could be also involved to improve diagnostics on shorts and open defects. So all in all, quick instruments are solving the top 3 problems identified recently, which are loss of test access in the first place, diagnosis and debug, and most important, testing high-speed links. All right, some target devices are on the board and directly addressable by instrumentation core, but some others, they are just the interfaces to the external world. So we need to be able to catch the defects in different I/O connectors. Here you can either use, well, in case of multi-board, the other counterpart of the board could be used as a counterpart tester. Matching boards or as simple techniques as looping back some some buses or adding some external testers is the way to get the complete coverage. So Quick Instruments essentially is a test solution with good coverage that you can get in just a half a day, and it addresses both your everyday testing needs and sophisticated quality issues. So let's have a brief look to some instrument examples we have in off-the-shelf toolbox. So of course, Flash programming is something that every test system needs to have, and we also have it providing very, very quick Flash programming and system programming on the board. Very popular instrument is the most simple one, which is the measuring the oscillator frequency on the board. Functional test doesn't provide this feature, but running the test on the board may depend on the PLL configuration and the right frequency data coming from the oscillator. So it's very important to check them before you actually do any tests. In terms of memory test, the typical application-based functional test will not boot if you have some issues on the memory bus. With Quick Instruments, you can diagnose the memory bus issues before you are running any software on the board. The most demanded instrument is the BERT. So you can measure in production for each and every board. You can measure I diagrams and get assessment of the soldering quality, signal issues on the board, especially for gigabit links, high-speed links. For Ethernet, we're providing very interesting feature, which is the firmware rate test, the stress test for Ethernet links that may detect wrong terminations or may detect some soldering issues on the PHY. Of course, simple buses like SPI, I2C, and so on, they also need to be covered. And of course, with application firmware, you can do that, but Quick Instruments provide an opportunity to work at the practical level, so you don't need to think of how you communicate to your peripheral devices, but you really need to just know what you do, streamlining the whole process. Some FPGAs have a processor part on top of just the programmable logic, and of course we are supporting the peripheral devices which are connected to the processor logic. One of the latest additions to the Quick Instruments portfolio is the family of radio frequency test instruments for the latest RF SoC families from Xilinx, for instance. Intel is also coming up with a similar device where you can test RF channels as such, as well as the specific dedicated clock pins of the RF subsystem. So to wrap up, that's a simple case study, which is a typical complex board that has a number of high-speed devices, and this is the test requirements you can see on this slide. And that is the solution that addresses these test requirements. We measured a performance with the customer, and we were able to deliver this solution in 2 hours, and the total board test time would be 2.5 minutes, which is also very, very good. Sometimes functional tests, they take maybe half an hour. Right, so all in all, since we learned all the difficulties that test engineers and board designers are facing, we delivered the framework that addresses all these issues, providing better quality in terms of testing, in terms of product, better performance in terms of test execution, as well as faster test development for test engineer, all in all, saving the cost and effort. So if you like our approach, challenge us, and we can think how you can benefit from these advanced technology and the advanced off-the-shelf framework, and save your costs. Thank you very much for your attention.